video, we are going to look at another technique in solving integral functions. We have looked at integration by use substitution, and also we have also done a lot of them, that is whereby we have two functions being multiplied, and that is integration by parts. Alright, now what if we have two functions being divided? For instance, let's make the numerator to be f of s and this is what g of s. When we have two functions being divided, how are we going to treat such case? For looking at what we have here, can we solve this by use substitution? You can see that it cannot. If we try to set u to be equal to the one here, that is s cubed minus s squared minus 6x. This, you are going to get 3s squared minus 2s minus 6. And that is not in this. So that is not going to help you. So you can see that use substitution will fail here. Integration by parts will fail here because no two functions being multiplied. Alright. So that is what the reason why we want to learn something about integration by partial fractions. Integration by partial fractions. And this is the idea. Every polynomial can be factored into a product of linear or irrational quadratic factors. That is as plus b and as squared plus bs plus c. Now take note of these two things. The first one is every rational, that is r of s is equal to f of s over g of s, where the degree of f of s, the degree, for instance this one, how you can see, where the degree, this is the degree of the numerator here is 2. And we always base on the higher degree, alright? Very good. So even if we have here to be, okay, even if we have here to be 3, we have here to be 4. We consider that the degree of the numerator here is what? 4. Very good. We will come back to it. Where the degree of f of s is less than the degree of g of s, can be decomposed into partial fractions. So now you can see that a rational function can be decomposed into a partial fraction if the degree of the numerator is less than the degree of the denominator. It is very important for you to take note of that. Very good. Secondly, for degree f of s, when it's greater than or equal to, don't forget, it's very important. When it's greater than or equal to degree of g of s, that is the one in the denominator, when the power or the degree of the numerator is greater or above or equal to the one on the denominator. That means that you do long division. That is, you do a long division. Now, let's revisit our algebra small. In case you remember your algebra, that is the same thing that we are talking about it here. Let's say that we have a function s squared plus 1, and we have s to the power 3 plus 2s squared plus 1. Now, since the degree of the numerator is less than the degree of the denominator here, we said that this can be decomposed into partial fractions. This can be decomposed into partial fractions. What is the reason? I wish I can ask you this question, but I hope you have answered me. The reason is just simple. The reason is just that the function that we have here is proper. The function we have here is proper because when the degree of the numerator is less than the denominator, that means that we are talking of proper fractions, proper functions, proper functions. All right. Now, what if we have x to the power 3 plus 2x squared plus 4x all over x to the power 3 plus x to the power 2, 2x plus 1. What if here you can see that the power of the numerator is greater than the power on the denominator? This means that you do long division. And the reason why you are going to do the long division is that, I hope you can tell me, it's just simple for it to be the reason that the function we have here is improper. And if it's improper, you can never, no, you dare not to decompose into partial fractions because it is improper. So it's unless you transform this to a proper function before you can now solve or decompose into partial fractions. I hope you are getting understanding. Very good. So this is when we say that improper is equal to the quotient. Write it down. It's very important. The quotient plus remainder over the divisor. This is what brought this. This is what brought this. All right. Improper like this. After solving it, you know that something like this. This is improper, so this is the function. The function will be here. That is the dividend. The dividend is what is here. That one will be here. Then the divisor is this one. So the divisor will be here. So this is the dividend, the divisor, the quotient, then the remainder. So definitely you will see that what you are going to get here is going to be proper because the remainder is always going to be less than the divisor. So you are going to get that place to be what? A proper function. And when you get it to be proper, then now you can decompose it into partial fractions. I hope you are getting understanding. Very good, very good, very good, very good. I trust you. All right. Now, there's one thing here that we have to be careful about it. It says for degree f of s greater than or equal to. It's not basing the idea only on when the degree of the numerator is greater than the degree of the denominator. Never. When they are equal to, it also means that you will solve it by long division. For example, if you have x squared plus 1 over x squared minus 1, then the power of the numerator is the same as the power of the denominator, even if we have 2 here or not. Our focus is the degree. Our focus is the higher one, degree. And such case is still improper. It's still improper. Even though the degrees are the same, but it's still improper. And if it's improper, then you use long division to reduce it so that we can base on the remainder over the divisor to solve it into a partial fractions. Alright, very good. So that is how it is. Sure, you will love it. Alright. So you see, you cannot forget your algebra as far as mathematics or as far as calculus is concerned. You can't forget your algebra. Alright, now with this integration by partial fractions, there are sometimes not all the rational functions that you have to solve it into partial fractions before you integrate. It's not all of them. There are some of them that you can split. There are some of them that you can split. And after this video, we will go on to that by splitting it. By splitting it. We will come back to that. But as far as this video is concerned, let's base it on partial fraction decomposition. So we are going to look at about 3 or 4 cases here in dealing with such case. So let's first look at the case 1. The case 1, that is called discrete linear factors. Discrete discrete linear factors. Discrete linear factor. That is when you have f of s over the g of s. Alright? Then that means that the denominator here is linear. When we talk of linear, you know what a linear means. A linear means linear. A linear means something which is straight. So you can see that all linear functions is having a power of 1. So for instance, y is equal to ax plus b. This is linear because the power is 1. Alright, so that is what we are talking about here. Very good. Now, and since it's linear, we can write a over the linear, which is ax plus b. Alright? Then plus b over ax 2 plus b2 plus it continues like that. Now that is just simple. Since it's linear, or since the denominator is having a power of 1, we treat it as linear. And treating it as linear is just a over that, a over that. Now that the a and the b is not a variable as you can see there, but it's a value that we have to go and look for it. It's a value that we have to go and look for it. Alright, so let's try our first question. Let's try our first question and you understand everything that we are going to do. Now we are saying that to integrate this, oh, I can't integrate that. Okay, then I will solve it to partial fraction. And when you get it to partial fraction, you can now come and integrate each term. It's the same thing as integrating the whole function. Let's look at one example under the linear factor. Sometimes I like to put it in the form denominator with a linear factor. Denominator with a linear factor. It's very good to do it that way. You can do that. Alright. So example. We have to integrate Alright, having this to integrate, then you can see that with this, your substitution will can help you. What else? Integration by parts. For all the techniques that we have learned so far, none of them is going to help you. Unless you solve by partial fraction decomposition. So now, looking at something here, look at something. You can see that the numerator, the power, the first thing to check is to check whether the degree of the numerator is less than the degree of the denominator. That is when you can now continue to resolve it to partial fractions. To resolve it to partial fractions. Very good. So, we write the function out. Let's forget the calculus here. We can't go with the calculus for now. We can't go with the calculus for now. Alright, so why? Okay, now, yeah, that's it. What is the degree of the numerator? You can see clearly that the degree of the numerator here is 0 because 1 raised to the power 0 is 1. So the degree of the numerator here is 0. Is it less than that of the denominator? Let's see. The question is, what is the degree of the denominator? Don't say 1. The degree of the denominator here is 2. You have to multiply this by this, and that is when you can see the degree of the denominator. So by multiplying this by this, you get s squared, and that's going to be the higher degree. Sometimes you not get it in a factorized form like this, but you just get it in a quadratic form. Make sure that you transform it back to its state before you start with whatever that you're going to do. Alright, so this we can see that it is proper. It is proper, so we can now express. So here, oh, this is linear because the degree is 1. So A over. There are two things to check with. First, whether it's proper or improper. And after identifying that it is proper, by taking the degree of the numerator and that of the denominator. After you are done, then you come back to express it. You come back to express it to partial fraction. So you can see that here it's having the power of 1. Then here is A over S plus 1 plus B over Y B again. This is having a power of 1. So you bring the B, then S minus 2. Now the A and the B, they are constant that we are going to find out. So this we are not doing calculus for now. What we are doing is what? Algebra. Very good. So you find the LCM. That is S plus 1, S minus 2. Alright. So this cancel this. This multiply this. To say that this is identical to this means that we can equate the numerators. We can equate the numerators. So here we get 1 is equal to, or 1 is identical to AS minus 2 plus B S plus 1. Alright. Now after getting this, we have two methods to do it. Whether by the elimination method or the substitution method. By the elimination method, you just ask yourself, what should I put S to be that can get rid of whether A or B? We can see here that when we put S to be equal to 1, here will be 2. That will not get rid of B. 1 here, that will not get rid of A. But when we put S inside here to be equal to -1, you can see that for -1, the inside here is going to be 0, and the inside here is going to be -3. But yes, so when here is 0, we can get rid of the B so that we can find our A. So here we get 1 is equal to A -3, sorry. And since this is 0, everything will go. So 1 is equal to -3A. So A is equal to 1 over negative 3 or negative 1 over 3. They are all the same. Alright, so that is what we are going to get for A. B. What will you replace S to B that can get rid of A in order for you to find B? You can see that when we put S to be equal to 2, this will go, but here we're going to take 0 here. So 1 is equal to A0 plus 2 plus 1, which is 3. So we get 1 is equal to 3B. Therefore, B is equal to 1 over 3. Therefore, B is equal to 1 over 3. So you can see that by elimination method, we have come out with the answer for the value of A and the what? And the B. Please, not forgetting that it's not only elimination method that you can use. You can go by substitution method. Substitution method. And how do we do the substitution method? There's another method, or should I say substitution? Not called a substitution method, but it's like this. You expand and simplify the right hand side. So after expanding and simplifying, you compare it to the what? To the left hand side. But normally, it becomes compressed when you keep on pressing forward with this is case 1. So there are some functions that when you go by that method, by expanding and simplifying the right hand side to compare the coefficient to the left hand side, it becomes somehow boring for you when you get about 3 equations or 4 equations to solve. So let's go by one method and go our way. All right. Anyway, the other method will be like this. 1 is equal to, then you expand and simplify this. Then you group like this. Then you factor S out. Now that you have expand and simplify the group like them for the right hand side, you now compare the coefficient. Don't forget that the constant we have here means that there should be a quadratic form in the left hand side, and that is AS squared plus BS plus C. Having only 1 here means that the coefficient of S squared is 0. The coefficient of S here is 0, and that here is 1. So when you are comparing coefficients, you can see that there is no coefficient of S squared here. So don't worry yourself about the left hand side. 0 will be equal to 0 because the left hand side, the coefficient of S squared is 0, and on the right hand side, the coefficient of S squared there is also 0. Alright, well, let's come to the S. The S here, the coefficient of the S here is 0, but the coefficient of the S on the right is A plus B. Equation 1. Then you go to the constants. Constants to constants. So the constant on the left hand side is 1, which will be equal to the constant on the right hand side, which is B minus 2A. Equation 2. Then you solve the 2 equations simultaneously. Then you solve the 2 equations simultaneously. That is why I'm saying that as you press forward, you will be getting more than 2 equations, sometimes 3 or 4, and it will become somehow complex for you that the elimination method is going to be simple. Alright. Now let's subtract, or we should add. We can subtract, but before we subtract, let's write it well. This is the same as a plus b is equal to 0. This is negative 2a minus plus b is equal to 1. So when we subtract, we are going to get 3a here. Again, so 3a here. This is 0 is equal to 1. So you can see that a will be equal to 1 over 3. That is why the here is negative, but let's take something there. There is something wrong there. This is that. And in it, where is the mistake coming from? Oh, alright, I can see where the mistake is coming from. Now, this one will be 0 minus 1. 0 minus 1. So here is going to be negative. Alright. In fact, it's a method. It's a method and it has to work. Alright, so you can see that with this, we are going to get a to be equal to negative 1 over 3. If you want to get b, you can replace the a that you have now by any of the equation here, and you are going to get b to be also 1 over 3. So that is how we solve the other method. But from now, I'm going to stick to one method and go my way. Alright. So after getting the a and the b, what is the constant? What are we going to do about it? What we are going to do about it is very simple. We are going to do the substitution back into this. So you come back. A is negative 1 over 3. B is 1 over 3. So you go and do the substitution 1 over 3. Alright. So what does this mean? This means that to integrate this as respect to s is the same as integrating the whole of this as respect to s. And here you can integrate it term by term and you go your way. So here is the same as integrating 1 over negative 1 over 3 s minus 2 plus 1 plus 1 over 3s minus 2 ds. And when you want to integrate this, you can integrate it term by term. So here you can make it, don't forget that there is a constant in here, that is negative 1 over 3. So we get this ds integrating term by term, 1 over 3. The constant will come out 1 over s minus 2 ds. And when you integrate this, you get negative 1 over 3 ln s plus 1 plus 1 over 3 ln s minus 2 plus c. Alright. And having this, you can see that you can rewrite this as half ln s minus 2 minus 1 over 3 ln s plus 1. So here when you factor 1 over 3 out, you are going to get ln s minus 2 minus ln s plus 1 plus c. And getting this we can combine this from your algebra that is going to be ln s minus 2 over s plus 1 plus c. So that is what we are going to get for that. So generally, or in general, we can deduce that in general, we can deduce that anytime you have integral of 1 over u square minus a, which is in the form of difference of two squares as respect to u. This is in the form of difference of two squares. It can be s squared minus a squared or 4s squared minus 9. This is still difference of two squares because you get 2s squared minus 3 squared. We are saying that this don't go by solving it by partial fraction decomposition. You can put it straightforward and get half ln u minus a over u plus a. So you can see that when you express this in a difference of two square form, you are going to get one to be plus and one to be minus. The minus will go to the top and the plus will come down. So for instance, if you have integral of if you have integral of 1 over 4s squared plus 9. This is 4s squared minus 9. This is the same as 2s squared minus 3 squared dx, and that is going to be equal to half don't forget that here you have to first set this to be equal to u. So if you put u to be equal to 2s, du will be equal to 2 ds. So ds will be equal to du over 2. Alright, so by substitution, you are going to get 1 over u squared minus 3 squared. I hope you can see that. And the ds here is du over 2. So we get half integral of 1 over u squared minus 3 squared du, which is going to be equal to half we are quoting because we are quoting this in this form. So this half will multiply half ln u minus 3 over u plus 3 because this is difference of two squares plus c. That is what we are going to be getting. That is what we are going to be getting. And this you get 1 over 4 ln u is 2s. 2s minus 3 over 2s plus 3 plus c. So straightforward, that is going to be your final answer for that. Very good. We are still under the case 1, and that is solving by discrete linear factor. Discrete linear factor. Let's try another question. Now, what if we have integral 4s squared minus 4s plus 6 over what if we have a question in this form? You can see clearly that the first thing to check, as I said previously, is that whether the power or the degree of the numerator is greater or less than that of the denominator. So here you can see that the degree of the numerator is less than the degree of the denominator. So this can be decomposed to partial fraction. All right. The next thing to check is that we want to see if we can see a linear factor in the denominator, whereby it's not so. We can see that. In fact, we haven't come to quadratic. When we get to quadratic, you will see that if you don't express it to the factorized form, you can't do it. All right. So we have to rewrite this. Then we factor it. So this is algebra. What we are going to do now is algebra. So if you want to factorize this, how are you going to do that? Alright. So you can see that with this, we can factor s out first. What is left? S squared minus s minus 6. Now we have a quadratic inside and we have s here. Very good. The next thing that we can do is that what is the factorized form of this quadratic? We can see that with this, we can factorize this to get. You can use a calculator to do that, or know that the coefficient is 1 multiplied by this, you get negative 6. With two numbers, when you multiply, you get negative 6, but when you add, you get negative 1. You can see that negative 3 and 2, right? I don't want to be taking you back to this thing. I hope you know it already. Alright. So that will be negative 3 and 2. So when you multiply this by this, you get this, and when you add, you get negative 1. Alright. So the factorized form of this is going to be s minus 3 s plus 2 s plus 2. Alright, so the factorized form is going to be very good, very good. So that's going to be the factorized form. Alright, is there any mistake? So let's solve it and see. S squared minus 3s plus 2s minus 6. So here we can factor s out here so that we get s minus 3 plus 2 out, s minus 3. So we get s plus 2, s minus 3. Oh, it's correct. It's correct. Very good. So to have this is the same as having it in this form. 4s so the function there, I don't want to bring the calculus. Let's put the calculus aside. You are dealing with algebra. Very good. So that is the rational function that we have, and we can see the factorized form of this. All right. Very good. Now, since we know that it's proper because the numerator, the degree is less than the denominator, we can now express this to partial fractions. So here we've come to a over this is another one, and the degree here is 1. And since the degree is 1, it's linear, so a over that plus This is also having a degree of 1, linear, b over s. This is also having a degree of 1. Alright. So even though we can't integrate this, but when we get this form, we can integrate it term by term for everything to be easy and precise for us. Very good. So we continue with our algebra. What is the LCM? The LCM is going to give you exactly what is here. So A will multiply very good. Now, since they are identical, we equate their numerators. After you are done, then we go by solving it in whether you want to go by expanding and simplifying the right hand side, then you compare the coefficients. Which one do you like? Alright, you can do it anyhow you like, but you can also do it in this form. You can see here that when we put x to be equal to 3, 3 here will be 0, 3 here, everything here will be 0. So putting x to be equal to 3 will help you to get rid of A and B, so that, sorry, A and C, so that the B will be free for you to find your P. So put x to be equal to 3. So that means that here 3 squared minus 4, 3. We know that when we put 3 here, everything here will be 0. So Charlie, I don't think there's a need for you to write it again. And here also the same thing. 3 here, everything will be 0. Don't write it again. For you not to waste your pen. For me, I want to maintain my marker. So with this, what I'm going to get, right? When you do everything, you are going to get B to be equal to 2. Do that. You are going to get B to be equal to 2. Now, after getting B to be equal to 2, check again. What will you put S to be? You can pause the video and solve it. You get B to be 2. Now check. You can see that when we put x to be equal to negative 2 here, A will go or vanish. Negative 2 here, B will also vanish, so that the C will be free for us to go and solve it. So we replace that by negative 2. Oh, we know that everything here will be 0. Everything here will be 0. What am I even writing? Okay. Everything here will be 0. Everything will be 0. You just write this. And when you solve for C, you are going to, after getting B and the C, we have to go for A. But you can see there is no number. What number again when you place, it will get rid of whether A, B, or C. 0. So when you place or when you put x equal to 0, you can see here will be 0, 0 because of the x here. To be 0, 0, and here you get negative 3 inside and 2 inside. So finally you get a to be equal to negative 1. Now, after getting a to be equal to negative 1, that is the end of the algebra. So what are we going to do about this negative 1? And what we are going to do is that we are going to replace. I would like to clean this part. You can pause the video and finish writing. So we now come back and rewrite that A is negative 1 over S plus B is 2 over S minus 3. C is 3. So what this means is that to integrate this as respect to ds, we are saying that it's identical to this. So what we generally mean is that we can integrate this also as respect to x. It's the same thing. So you see now it's simple. But to integrate the whole function like this, it's going to be complex. So you substitution can't even help you. So the only thing that you do is partial fraction decomposition. Alright. So here you integrate it 10 by 10. When you integrate this, you get negative 1 over s ds plus 2 out 1 over s minus 3 ds plus 3 out integral of 1 over s plus 2 ds. So here we get negative ln x plus 2 ln s minus 3 plus 3 ln s plus 2 plus c. Woo! Right. So that is the end of the question. And you can choose to continue to simplify it. Yeah, you can. You can. You can choose to continue to simplify it. It's still the same thing. Alright, so let's go to our next case. And that is, we have looked at the linear factor. The linear. Let's go to the another part, which is dealing about the case where the power of the numerator is greater than that of the denominator. That is improper. But before that, I would like us to look at one more thing. Yeah, let's look at one more thing. Case 2. The quadratic factor. The quadratic factor. All right. So we now look at the quadratic factor. And what we are saying is that for the quadratic factor, it's not anything, it's not that difficult, it's just simple. It's the same thing, the same idea. We are going to have a function over another function. But this g of x, where g of s is in a quadratic form. It's in a quadratic form. It's in a quadratic form. And when it's in a quadratic form, this is going to be identical to as plus b over that quadratic. Let's say as squared plus b. Since the power here is 2, it's not 1. If it's 1, it's linear. Since it's 2, it's going to be as plus b, not just a over that, but as plus that. Very good. That you know from your algebra already. That you know from your algebra already. Alright, so let's look at our first example here. We are to integrate. We are to integrate dx over x to the power 3 plus s. Now, this is the same as integral of 1 over here. To make it clear to you, try to factor out the denominator. Always we factorize the denominator. When you factorize that, you get s plus 1, s squared plus 1 ds. Now, you see, new substitution will not help us, none of them will help us. So let's bring out our function back. And this is going to be identical to, now watch. You can put this one inside of a bracket, and this is raised to the power of what? 1. And for that matter, this is going to be linear. So a over x. I hope you can see that. Now this is what? Having a power of 2. So that is in the form as squared plus b. So that is quadratic. Never confuse yourself that, yes, always a quadratic is in the form as squared plus bs plus c. But the case where the b is 0, this part will not come. And that is the same case here. You can see the constant c to be 1, but this is not there. It doesn't mean it's supposed to be a quadratic. It's still a quadratic. So here you get bs plus c over s squared plus 1. Very good. Then we find the LCM, still on the algebra part. So the a will multiply s squared plus 1 plus bs plus c will multiply the s. Okay. To say this is identical to this, that means that we can equate the numerator. So we get 1 is going to be identical to a s squared plus 1 plus bs plus c multiplying x. So we get here, by elimination or expanding and simplifying it, it depends on you. Anyhow you would like to go about it. You can expand and simplify and compare the coefficients. Or here you can see that when we replace x, don't forget this is c. When we replace x by -1, you are not going to get 8. The only value that can help us here is 0. And only 0 is not 1. So let's expand and simplify and go away. So here you get s squared plus a plus bs squared plus cx. So 1 is going to be identical to, or 1 is equal to AS squared plus BS squared plus A plus C so there is another quadratic BS squared plus CS plus A. So this is going to be identical to factor S squared out A plus B plus the coefficient is C plus A, which is the constant. So now you can now compare coefficients. Alright. The coefficient for S squared here is 0. So A plus B is equal to 0, equation 1. The coefficient of the S here is also 0. C is equal to 0, equation 2. The coefficient of the constant A is 1, so we get it 1. So now we know that our C is 0, our A is 1. So we can go for B. So A plus B is equal to 0. We know A is 1 plus B is equal to 0. So B is going to be negative 1. So don't forget, A is 1, B is negative 1, C is equal to 0. This from your algebra that you know already. We are just applying the idea. Now, after you are done, then you go and do the substitution. So we come back to this part. A is 1, B is negative 1, whereby we don't write the 1. C is 0. So this simplifies to 1 over S minus S over S squared plus 1. Alright, very good. So to integrate, then integrate each term. I hope you can see it's simple. Then we are going to keep it term by term. Integrate 1 over S ds. Integrate S over S squared plus 1 ds. So this is going to give you only S. Simple. What about this one? Don't forget. Here we are going to let U to be equal to S squared plus 1. Because the 4 here is 1, the 4 here is 2. So when you take U to be this, you take the U to be equal to 2S ds. Use substitution. So ds is going to be du over 2x. So by substitution, s over u multiplied by du over 2x. This take away this. We get half integral of 1 over u du, which is half ln u. But we know that the u is s squared plus 1. So we get that is all. Alright, so I can now clean it that our result, our answer for or the integral for this is going to be that. Don't go and work this one in exam. Don't go and work this one somewhere and bring back the answer. Do it in your booklet, your answer booklet. It's also part of the marking. And you can reduce it, you can make it mean S over that. But don't forget that this half will raise the power of this. So you're going to get something like s over s squared plus 1 to the 4 half plus. Alright. So that is that. So that is that for the quadratic. Let me see if I can get one more question under the quadratic part. We can have integral of wow. So having these questions to solve, the first thing to check is it having a degree of a numerator being less than the denominator? Truly yes. The degree here is 2, the degree here is 3. Then we can resort to partial fraction. Alright. But we need to factorize the denominator so that we can appreciate the beauty of the function. Alright. So we go and apply our algebra. Alright. So when you are to factorize this, how are you going to do it? Here, simply you can see that with this you can write it as 2s squared minus s squared plus 8s minus 4. Here we can factor s out here and we get 2s minus. We get, alright, so we get 2s squared minus, we can factorize s squared rather. We can factorize s squared out here. S squared. So we get 2s minus 1. Very good. Plus, here we can factor 4 out. So we get 2s minus 1 also there. Very good. So you can see that there is 2s minus 1, 2s minus 1. I hope you are not confused. This and this, we can factor s squared out. So we are going to be left with 2s here, and here we are going to be left with 1. This and this are the same. So the factorized form is s squared plus 4 and 2s minus 1. That is going to be the factorized form. So to bring out the function to solve by partial fraction, you are going to get this. Very good. So now you can see that this is where the case where we are having a denominator to be a quadratic factor is coming in. You can see that this is having a power of 2, so it is what? Quadratic. But this is not quadratic because this is having a power of what? 1. Alright. So that is going to be in the form. So this is going to be identical to, there is a quadratic here. So as plus capital B over s squared plus 4 plus what we have here is not quadratic, it's linear because the power is 1. We don't care about the coefficient. So C over then we find the LCM. So this is going to multiply 2s minus 1 plus C will multiply s squared plus 4. Since this is identical to this, we can equate the numerators. Very good. So now, having this, then we go by which one do you like? Simultaneous, the one that we do together with simultaneous or what? Anyway, let's see if the elimination is going to be easy for us. You can see which number are you going to replace here to get rid of something. There is none. The only thing that we can do is 0. And when you replace 0 here, 0 here will take away this, but we like B and C. So you can see that the elimination method is going to be easy, alright, but in this case, we will end up by expanding and simplifying at the end because the 0 will get rid of only this A, but the C and the B will still maintain. You will not get any number to do substitution again after that. So let's expand and simplify and compare coefficients. Alright. So you can pause the video and expand and simplify it. I'll come back to give you the term so that we compare. So when you expand and simplify, you are going to get, make sure you have done it. Yeah, it's minus B. Minus B plus 4C. Alright. So when you expand and simplify, you get the quadratic to be in this form. So you compare by this. This is 1 minus 1s minus 21. So for the s squared, you are going to get 2a plus c, that's the coefficient of the s squared, to be equal to the one here, which is 1, equation 1. Then you move for the coefficient of s, which is 2b minus a, which is equal to negative 1. It's not 1, it's negative 1. Equation 2. Then the coefficient of, that is the constant itself. So that is minus b plus 4c. And that's going to be equal to negative 21, equation 3. Very good, very good. So now, I'm coming. Alright, so from where we are, you can use, you can choose equation 1 and 2. Alright, you can make A the subject in equation 1. You can make A the subject, or make A the subject in equation 2, and then do the substitution, so that you are going to get You see, the equation 3 is in the form of B and C. Alright. So in equation 1 and 2, we want to get rid, you have to get rid of the A so that you get a new equation which is also in the form of B and C to combine with equation 3 and solve it simultaneously. Alright, that is what I mean. Let me help you small. So from equation 2, we can get A to be equal to sending A here, 2B plus 1. Hope you can see that 1 is here and it's 3. Alright. So then we replace in equation 1. When we replace that in equation 1, we are going to get 2A. Equation 1, 2A. A is plus C equal to 1. So we are going to get 4B plus 2 plus C is equal to 1. So 4B plus C is equal to 1 minus 2. So 4B plus C is equal to negative 1. Equation 4. So you can now see that equation 3 is in the form of B and C. And equation 4 is also in the form of B and C. So you can treat these two equations simultaneously and you are going to get B and C. And after getting B and C, to get A, replace the C value in the equation 1 and you are going to get that of the A. So I'm going to give out the answer straightforward and go my way. Alright. So when you do that, you are going to get A to be equal to 3. You can pause the video and continue to solve equation 3 and 4 simultaneously. Whether by substitution or elimination method, you get that. B to be 1, C to be equal to negative 5. Alright, so that is that. Then we go and do substitution. So I would like to do in this part. Make sure you pause the video and write. So our reason for applying all those algebra is to get C to be equal to negative, is to get A, B, and the C. So we are now going to do the substitution. A is 3. 3s plus B is 1. 1 over s squared plus 4 plus C negative 5. So the negative affects this. Then to integrate this as respect to ds, the same as integrating this as respect to x. So let's make it 10 by 10. 3s plus 1 over s squared plus 4 ds. And also integrating minus integrating this here, we can bring out the 5. 1 over 2s minus 1 ds. Now, to integrate this, there is no problem about it, okay? Here you can make it 5 over 2 leave 2s minus 1 plus c. that if the coefficient is here, it's going to divide whatever is here. That's why the general form is 1 over A. So that is that. But with this part, to integrate 3x plus 1 over x squared plus 4 dx, we have to split it. And how do we split it? It's just simple. This is the same as 3x over x squared plus 4 plus 1 over x squared plus 4 dx. You can see that to write, forget about the calculus, forget about the integration. To write this function, it's the same as writing it like this because they are sharing the same denominator. So you just add the numerator and maintain one denominator. So you just add the numerator and maintain the denominator. So this is the same as this. And we can now integrate this. See, this is going to be 3 that of x over x squared plus 4 dx. This is u substitution. And that is going to give you, I would like to quote it straightforward and go my way. No problem. Let's do it. U is equal to x squared plus, please don't forget, this part is what we are treating now here. So du will be equal to 2x dx. dx will be equal to du over 2x. So you go and do the substitution back. I don't want to clear this part. Three x, the whole of that is u, times dx. dx is du over 2s. S cancel s. 3 over 2 integral of 1 over u du. 3 over 2 integral of u h1 negative 1 du. So this is 3 over 2. To integrate this, no need for you to bring it in this form. That's going to be 3 over 2 leave u. And that is 3 over 2 leave x squared plus 4. So that is for only this. This split to get this. This resolves to this. Now what again? Now you can see next time don't be going by all these processes, alright? You can get the answer simple. You know that this is 2 squared, alright? So it is like this. Oh, this is what I mean. So it's like this. This is 2 squared. So it's going to be this 3. If there is no coefficient here, it's going to be 1 over the 2, which is the square of this. 1 over the 2 leave of this. So that you don't do it. Sometimes you have to go by the technique, okay? 1, let's assume nothing is here. Or if you have integral of 1 over u squared plus a squared. This is going to give you 1 over 8. How would I say? Leave u squared plus a squared. Right this now it will help you, alright? Next time I'll just jump and go without going through the step. Let you be this, that. Next time we'll do that. Very good. So if there is coefficient here, that will come here. Like what we are having there. Very good. Now, what about this? We are like this. This is just this. So what about the integral of this? So what about the integral of this? The integral of this is just tan inverse. Remember, don't forget it all. Tan inverse. We established that if you have something in this form, when we're doing integration by inverse straight substitution or whatever, there's something like that. This is going to be tan inverse of u. Don't forget, that's going to be tan inverse of u. But if it's in a general form like this, here, if here is 1, you just get tan inverse. But if it's in a general form, this will be 1 over a, then here you get that is the general form. Okay, that is the general form. If here is 1, here will be 1, so here is not important. Here will be 1, so here is not important. That is why if it is integral of 1 over x squared plus 1 is tan inverse. 1 over x squared plus 1 is tan inverse. But if, for instance, what we are going to do right now is, this is integral of 1 over x squared plus 2 squared dx. So here, the a here is going to be 2. So the answer is 1 over 2 tan inverse of u. The u is s over 2. Very good. Very good. Very good. I love mathematics, especially when it comes to calculus. So now, this is what we are doing. This result is correct. But with this, we have to come back and split it, solve this to get. So if you know it's okay, you know that when you split this is going to be 3 over, here is 2 squared, so 2. Ln x squared plus 4. And that is exactly what we have here. Then plus, and that is 1 over 2 tan inverse, this minus, tan inverse of x over 2. So that is going to be the final result, for integrating this function, for integrating that function. I hope it's not difficult. Take your time, go through it, try and replay it back, and everything.